Welcome to the Deep Dive. Today, we are taking a stack of sources that look at, well, one of the biggest paradoxes in modern technology, artificial intelligence.
It really is a paradox.
On one hand, AI is probably the most powerful tool ever introduced for cybersecurity. And yet, at the same time, it's also the largest new risk surface we have to manage.
It's a truly transformative moment. I mean, AI isn't just optimizing our existing defenses. It's fundamentally changing the whole calculus of security operations.
The whole game.
The good news is it offers this incredible augmentation. It allows human expertise to scale far beyond what we thought was possible. But, and this is the big but, the immediate challenge is that it introduces entirely new threat vectors.
Right, and it lowers the technical barrier for attackers all over the world.
Exactly.
And that dual nature, that's what makes this topic so urgent. Our sources really confirm this isn't some problem for the future. It's happening right now.
Yeah.
We're seeing statistics that highlight this massive potential and the massive unpreparedness. For instance, the IT firm Capgemini reports that 2/3 of organizations are already prioritizing AI in their security ops.
So they've bought into the tool.
They've bought the tool, now they need the instructions and the security controls.
And that's the part that often lags behind adoption. The World Economic Forum's Global Cybersecurity Outlook, it reveals this massive preparedness gap.
Okay, so what does that gap look like?
We know the threat is coming. I think it was 66% of organizations expect AI to significantly impact cybersecurity,
Right.
but only 37%. Just 37% evaluate the security of their AI systems before they deploy them.
That is staggering. So you have almost 2/3 of the world bracing for impact, but only a third are actually, checking the integrity of the system before they push it to production.
It's a huge blind spot.
And that gap is only getting more urgent because of generative AI. I mean, Bain & Company reports that 95% of U.S. companies are now actively using it. Adoption is just soaring.
It is. And we have to catch up on the security and governance side of things, like yesterday.
Right.
Absolutely. And that urgency, that really defines our mission for this deep dive. We're going to try to synthesize the opportunities and the challenges by looking at this through 3 critical interconnected lenses.
Okay, let's lay them out.
First, we have to secure the generative AI applications themselves. That means the models, the data, the agents, all of it. Second, we'll look at how we can use this technology to actually strengthen our overall security posture, to scale our human expertise.
And the third.
And third, we have to understand and protect against the increasingly sophisticated generative AI-powered threats that are being launched by adversaries.
So we're going to walk you through the architecture, the critical weaknesses that are just inherent in large language models, and then the essential role of mathematical certainty through something called automated reasoning.
And finally, the strategic frameworks you need to manage all of this complexity.
All right, let's get into it.
Let's do it.
To start this journey, I think we have to talk about language. In the press, we often hear the terms AI security and AI safety used almost interchangeably.
They get mixed up all the time.
But they are very distinct concepts, and they serve fundamentally different purposes in building a trusted system.
That distinction is paramount. When we as security professionals talk about AI security, we're really focused on the classic cybersecurity goals. We're protecting the AI system itself.
So the hardware, the software.
The hardware, the software, the data, the model, weights all of it. From unauthorized access, from tampering, theft, or data exfiltration. The objective is to maintain confidentiality, integrity, and availability.
The CIA triad, the classic.
The classic CIA triad. So AI security is the shield against a deliberate attack or subversion.
Okay, so if a threat actor tries to, say, hack the hosting infrastructure to steal training data, or if they try to change the model weights to poison future outputs, that falls squarely under AI security.
Exactly. It's a deliberate cyber attack against the AI asset.
Got it. So what about AI safety?
Now, AI safety is far broader. It involves ethical use, minimizing potential harm, and making sure the system operates as was intended without causing, unintended societal damage.
So it's less about the outside attack and more about the internal behavior.
Precisely. Safety addresses those internal factors, unintended behaviors, biases, or operational flaws. This is where you implement guardrails and careful fine-tuning to ensure the system is reliable and ethical in its operation.
I see. So if AI security is the padlock on the door preventing a deliberate break-in, AI safety is more like the architectural design review that ensures the building doesn't accidentally collapse on its own.
That's a perfect analogy. Or that it doesn't recommend shutting down critical infrastructure or generate overtly biased content. It's about preventing the system from malfunctioning or causing harm unintentionally.
And you need both.
You absolutely need both to establish what we call responsible AI. You need a secure system to prevent external compromise, and you need a safe system to ensure trustworthy operation. Only when you have both can you really build that societal and operational trust required for mass adoption.
That makes sense. Let's also ground ourselves by differentiating between the new technology we're focused on today and the machine learning systems we've been integrating for years.
Yes, this is a crucial distinction, especially in terms of risk. Classical machine learning, for the most part, makes predictions or classifications based on existing data.
So like classifying an email as spam or predicting when a piece of equipment might fail based on its sensor readings.
Exactly.
Yeah.
It's analyzing existing content and then making a decision based on patterns it has seen before.
But generative AI is fundamentally different. It's right there in the name. It creates new content.
Yes. It can write human language, it can draft entirely new source code, it can generate these incredibly sophisticated digital images and videos.
And the moment the technology shifts from just analysis and prediction to autonomous creation.
The security surface area changes dramatically. New pathways open up for data to flow, and you suddenly have to worry about the security implications of novel, malicious outputs, like highly realistic deepfakes or complex attack code that's generated in an instant.
And here is the massive critical takeaway for you, the listener, especially if you're worried about having to throw out your entire existing security investment.
Just don't throw it out.
You absolutely do not need to reinvent security from scratch just because of generative AI.
That's so right. If you have robust security fundamentals already in place, strong identity and access management, comprehensive log monitoring, mature data classification policies, a well-tested incident response plan.
The basic.
The basics. If you have those, you have the solid foundation upon which generative AI security must be built. You're just adapting and applying those controls to new technology. You are not starting over.
The principles of good security are timeless. Okay, building on that foundation, let's dive into the architecture. We need to really understand the components we're trying to secure and, critically, this shift that's creating entirely new security concerns. The move to agentic AI.
Right. So when we talk about a generative AI application, we're really talking about several interconnected layers. At the very core are the foundation models, or FMs.
These are the massive models trained on just colossal data sets.
Colossal data sets. They provide the base intelligence and sort of general knowledge.
And from that base, we get the specialized forms we hear about every single day.
Precisely. The large language model, the LLM, is a foundation model that specializes in human language, code generation, and understanding text-based configurations. Then you have large multimodal models, or LMMs, which extend that ability to process and generate sound, images, or video.
The process where the model takes a user's prompt and generates an output, that's called model inference.
That's model inference.
So that query response loop print in, inference output out, that's the traditional interaction model we're all used to. But our sources highlight that the security world is rapidly shifting beyond that simple exchange.
It's moving into something much more autonomous. Agentic AI.
How does this fundamentally change the security equation?
Agentic AI systems use those foundation models not just to answer questions, but to orchestrate complex tasks. They move beyond a basic query and response by interacting dynamically with external data sources, connecting to external tools, calling APIs.
And chaining multiple model interactions together.
Yes. So unlike traditional rule-based software, which just follows these predefined static pathways, agents operate in a much more human-like, autonomous, and goal-driven fashion.
And this shift from just retrieving information to dynamically carrying out actions, that's a giant leap for security complexity. I saw a Gartner projection that by 2028, a third of enterprise software applications, 33%, will include agentic AI.
Which is up from basically 0 today.
Virtually 0. And it gets crazier. They expect 15% of day-to-day operational decisions will be made autonomously by these agents.
That transition from AI that answers to AI that acts is the critical challenge we have to secure. In the security domain, you can imagine agents handling repetitive alert triage or even initiating automated vulnerability scans.
Which sounds great.
It sounds great, but because they are taking action-invoking APIs, accessing sensitive databases, coordinating with other systems, the risk profile just multiplies exponentially.
This raises a massive concern around identity and permission. I mean, an agent is acting on behalf of a caller, either a human or another machine, and that agent needs permissions to complete its workflow.
Exactly.
But if that agent has too much privilege or if the security context somehow gets lost mid-workflow, the potential for unauthorized action is just enormous.
It's huge. We now need this really granular approach to managing user identity, machine identity, and tool access all at the same time. If an agent calls a database, then uses that data to call an API, and then uses that output to call a third system,
The chain can get really long.
the system has to maintain the security context and the authorization level of the original caller through that entire chain. If the agent itself is compromised or just given excessive privilege, it can execute these runaway tasks that traditional security controls were never designed to catch.
So what's the solution?
It requires robust, continuous validation of authorization at every single step of the agent's journey.
Okay, so once you understand the risk of the agent, the next step in securing Gen AI is to accurately scope your implementation. As our sources confirm, not all Gen AI is created equal.
Not at all, and knowing your scope is vital because it directly determines your security responsibilities.
So how do we classify these use cases?
We can classify them based on how the organization interfaces with the application and what data is used. To simplify, we can think of it as two broad mindsets: the buyer and the builder. These often represent different scopes in an organization.
Okay, let's start with the buyer's mindset. This would cover, scopes 1 and 2?
Yeah,
Consuming existing off-the-shelf AI services.
exactly. You're using a vendor's public API, a web application, or a mobile interface. You are essentially just renting the intelligence.
So in the buyer's mindset, your security responsibility for the underlying infrastructure, the model training, all that heavy lifting, that's reduced.
It's significantly reduced. The service provider handles that. However, and this is critical, your responsibility for data handling, compliance, and access controls remains absolutely paramount.
So you still own the data risk.
You still have to control what proprietary data your employees are putting into it, ensure that data is classified correctly, and manage how your specific users are authorized to interact with the service. The data plane is still entirely your risk.
And then there's the builder's mindset. This covers scopes 3, 4, and 5, where you're building custom AI applications, fine-tuning foundation models with your own data, or even training your own models from scratch.
Right. And when you move to the builder's mindset, your security responsibility just expands dramatically across the entire stack. You inherit the risk of securing the training data itself, protecting the model artifacts, the actual outputs of the training process, and maintaining the security and integrity of the hosting infrastructure where the inference happens.
This perfectly illustrates the shared responsibility model in action. The security boundary shifts based on your implementation scope.
Absolutely. If you're a buyer consuming a public API, your focus is narrow: data, ingress and egress controls, user IAM. But if you're a builder training your own model on, say, PII, you inherit these massive responsibilities for securing the training environment, protecting against data poisoning attacks that could corrupt your model before it ever sees production.
And managing the entire lifecycle of that model artifact.
Right. Understanding these scoping differences is the very first step in correctly budgeting your time and resources for implementing the right controls.
That structural understanding really sets the stage for the core security challenges that are inherent to the technology itself. We've identified 3 critical, non-negotiable concepts that define why securing LLMs is just fundamentally different from securing traditional software.
And if you miss these, your controls will fail.
Because they force us to assume the model itself can't be trusted with enforcement.
Exactly. We have to architect our defenses externally.
Okay, so let's start with the first concept. LLMs are functionally non-deterministic systems. This is the complete opposite of traditional software, which is predictable.
That's the problem. In traditional code, A plus B always equals C. Always. In an LLM, if you give the model the exact same input twice, you can still get 2 different outputs.
And that's on purpose, right?
It's intentional. It's due to settings like the temperature and sampling methods that inject a bit of randomness to make the output more creative. But this variability is a massive challenge for security controls. If a control relies on consistent, reproducible behavior like the model always filters a certain malicious phrase, it will eventually fail.
So we can't rely on the LLM to consistently perform security filtering. Critical operations, like financial transactions or system changes, they must have validation checks implemented externally.
You can't trust the model to behave the same way every time. Precisely.
Wow.
Now, the second critical concept is maybe the most dangerous. LLMs process all inputs with equal privilege. This is an architectural reality.
What does that mean, equal privilege?
Whether it's the developer's system prompt that's setting the rules, or the user's input, or documents retrieved for context in a RAG architecture, or outputs from external tools, all of it is just converted into undifferentiated tokens that are processed by the same attention mechanisms.
Wait, so if everything is just undifferentiated tokens, that means there are literally no security boundaries inside the model itself. Nothing to separate the instruction from the data.
Architecturally, zero. This makes it impossible to implement authorization or access control inside the model. If a malicious user input, a prompt injection is treated with the same weight as the internal system prompt that sets the safety rules.
The user's input can just override the intended behavior.
Which is why prompt injection works so effectively. Authorization and access controls must therefore always be external, sitting outside the model to protect its integrity and prevent malicious token manipulation.
That's a powerful insight. So the final concept is that LLMs are fundamentally statistical pattern completion engines. They're not logical deduction machines.
Correct. Their output is based on recognizing and extending patterns they learn during massive training. They look for the statistically most probable next word or token. They do not possess logical deduction or any real verification of truth.
And this is why we see hallucinations.
This is exactly why. You get these outputs that are incredibly convincing, perfectly structured grammatically, but they're just factually incorrect. Because they lack logical consistency, they can't maintain accuracy or policy compliance across complex, multi-step operations without help.
So these three concepts, non-determinism, equal privilege processing, and statistical generation, are the architectural vulnerabilities. They force us to mandate external security boundaries and defense-in-depth strategies because the model itself is just inherently untrustworthy for security enforcement.
Given those inherent limitations, we have to move into concrete implementation strategies. We've identified 9 key pillars of best practices for securing these applications, but we need to focus on how GenAI changes the way we implement them.
Okay, pillar 1. Take a secure-by-design approach. This is always true, but how does the GenAI pipeline complicate this?
It forces us to broaden the design scope. Secure by design means integrating security from the initial design all the way through deployment. But for AI, this now includes securing the entire data supply chain.
So from sourcing the training data through the fine-tuning environment and into the deployment infrastructure.
The whole thing. Tactics like using memory-safe languages and continuous patching, those are table stakes. Frameworks like the NIST Secure Software Development Framework and its new generative AI profile provide excellent guidance on how to integrate security throughout this really complex AI lifecycle.
Pillar 2 is implementing comprehensive access controls. Given the complexity of RAG architectures and these autonomous agents, this is where identity becomes a nightmare.
It really shifts from user identity to machine identity management. We have to apply the principle of least privilege, not just to our human users, but across all the components. The models, the data stores, the endpoints, and critically, the agent workflows.
And for RAG systems.
For RAG systems, you need multi-layered access controls to ensure the model only retrieves data that the human user is actually authorized to see. And for autonomous agents, you have to establish unique machine identities with granular authorization levels. An agent that only pulls data should never have write permissions to a production system.
Common sense, but hard to implement. Pillar 3 focuses on secure data and communication flows.
The key GenAI twist here is preventing data exfiltration during inference. We need to ensure that proprietary data being used for grounding or sensitive prompts never leave the private network boundary.
So solutions like private network endpoints are essential?
They're essential. Something like AWS Private Link is a prime example. They encrypt network data and isolate the model traffic. Furthermore, input sanitization has to be rigorous, and prompts themselves should be managed in secure catalogs, treated just like sensitive configuration files.
Next, we have to monitor and audit events. And this isn't just about traditional logs anymore, it's about the model's behavior.
This is a major pivot. Traditional monitoring tracks authentication and infrastructure exploits. Gen AI demands monitoring of the data plane and the control plane for entirely new behaviors.
Like what?
You have to track token usage. If you see a sudden spike in token consumption, that could indicate a prompt injection attack trying to force the model to regurgitate training data. You also need to track hallucination rates, unusual access patterns, like an agent suddenly accessing a database outside its defined scope and potential data leakage within the generative flow itself.
That sounds like it needs specialized tools.
It requires specialized AI observability tools. This kind of nuanced monitoring is beyond what traditional systems can do.
Okay, Pillar 5 deals with controlling AI system behaviors through defined guardrails.
Since the model itself is non-deterministic, guardrails are essential external boundaries. They define the limits for how the AI system interacts with data and executes workflows.
Mhm.
This includes response validation like simple keyword filtering or human review, but most rigorously automated reasoning, which we will deep dive into in a bit.
And RGAG architectures are a form of guardrail too, right?
A highly effective one. Using ARGA, which limits the model's knowledge to specific controlled knowledge bases, is a great guardrail against generalized misinformation.
The 6th pillar addresses the pervasive and difficult threat of prompt injection by focusing on securing system and user prompts.
This is a top-level concern. The OWASP Top 10 for LLM applications proves this. We need strict operational procedures. This means maintaining a managed prompt catalog with least privilege access, implementing robust sanitization of user inputs, and crucially, validating prompts before they ever reach the model.
How do you validate a prompt?
You can use techniques like keyword searches for known attack phrases, and there's a more advanced technique of using an LLM as a judge input filter, where a small, secured model validates if the user prompt is trying to breach the system prompt's boundaries. We have to enforce clear context boundaries within prompt templates.
Pillar 7 is critical for managing the risk of autonomous AI, preventing excessive agency.
Since agents shift from advising to acting, we have to institute strict controls. Set clear permission boundaries for agent workflows. Limit the agent's access to only the minimum necessary systems and data sources it needs to complete its task.
And because they're automated, you need throttles and alarms.
You have to. If an agent starts an automation loop, maybe calling itself, or an external tool, over and over throttling and immediate alarming are essential to prevent runaway tasks, massive costs, and potential unauthorized system changes.
For builders, Pillar 8 is crucial. Detect and remediate data poisoning risks.
If you are training or fine-tuning a model, the security of that data input is paramount. Isolate your training environments from production. Implement stringent data cleaning processes before training begins, including toxicity detection and bias scans to make sure malicious or harmful data doesn't corrupt your model's integrity.
Because poisoning a model can lead to these long-term backdoors that are incredibly hard to find later.
Incredibly hard to root out.
Exactly. And finally, Pillar 9, conduct penetration testing. You have to continuously test these evolving systems.
Regular red team exercises have to probe not just the perimeter, but the AI models themselves for weaknesses like prompt injection vulnerabilities, data leakage through outputs, and denial of service vectors. And since these systems are so dynamic, automating that penetration testing provides a continuous assessment loop, which is vital for maintaining your security posture.
And there are resources for this.
Yes, organizations should actively consult resources like the OWASP Gen AI Security Project, including their guides on agentic AI threats, to structure these rigorous testing programs.
Okay, we've established that LLMs are statistically driven, they're non-deterministic, they're prone to hallucination, they lack logical certainty.
Right.
That deficiency drives us to one of the most intellectually rigorous solutions available, automated reasoning, or AR, sometimes called formal verification.
This is the essential complement to probabilistic AI. When correctness is non-negotiable, when the answer must be 100% right, like in financial or security operations, we just cannot rely on a statistical engine. AR is how we bridge that gap from prediction to mathematical proof.
So for listeners who might not have encountered this concept before, what is automated reasoning exactly?
AR is a technique that uses sound logical rules and symbol manipulation to construct proofs. It's the application of mathematics and formal logic to complex digital systems. It moves beyond checking if a system seems right to proving if a system must be right.
Let's return to your Pythagorean theorem analogy to really drive home the difference between logic and statistics.
Think about it this way. When mathematicians proved that a PR plus B equals CEC for all right triangles, they didn't go out and measure every right triangle in the world.
That would be impossible.
Impossible. They used a logical deduction proof. This single proof covers an infinite set of possibilities with 100% certainty. Automated reasoning takes that same approach proof by logical deduction and scales it up for complex software systems. It moves beyond trying to check every scenario and proves the correctness for every single possible scenario using mathematical logic.
This makes the differentiators between AR, traditional machine learning, and traditional testing crystal clear, especially for critical systems.
They're completely distinct paradigms. Machine learning provides a probabilistic prediction based on the data it has seen. It might be 99% confident, but it will never be 100% certain, and it's always susceptible to bad data.
Whereas automated reasoning,
Automated reasoning, on the other hand, provides mathematical proof through logical deduction. It is completely independent of training data quality and provides certainty based on formal logic.
and compared to traditional software testing, which we rely on so heavily today.
Traditional testing unit tests, fuzzing, audits, it validates system behavior under a finite number of specific scenarios that a human thought to test. It gives you confidence that the system works in the ways you tested it.
But not in all ways.
Not in all ways. Automated reasoning verifies system behavior under every possible scenario that can be modeled. It provides mathematical certainty that a property will hold true regardless of input variations.
Certainty is powerful.
Yeah.
Let's walk through how this actually works as a crucial external guardrail in a probabilistic system. Let's use that airline refund chatbot example.
Okay. So when you deploy an LLM for a high-stakes, policy-driven task, you have to wrap it in AR. The process is threefold. First, you build a formal model of the specific domain, the airline's refund policy expressed in mathematical logic from the official system specification.
So you're translating the policy into math.
Exactly. Second, you document all the environmental assumptions in mathematical logic. Third, the AR system then acts as a logical gatekeeper, proving if an LLM-generated assertion is valid, invalid, or conditionally valid.
Okay, so our policy is full refund if a segment is canceled operationally, but not if it's weather-related. Let's say the LLM answers a customer inquiry with, yes, you get a full refund.
The AR guardrail immediately verifies that statement against the formal policy model. In a success scenario where the cancellation reason is indeed operational and non-weather related, the AR system checks. Is the segment canceled? True. Is the reason operational? True. Is the reason not weather? True.
All conditions are met.
Since all conditions are logically satisfied based on the formal model, AR verifies the yes answer is correct and allows the LLM output to be passed to the user.
Now, the critical hallucination-prone scenario. Suppose the flight was canceled due to weather, but the statistical LLM still predicts the word yes because it's a common answer in customer service dialogues.
The AR system evaluates the same conditions. Is the reason operational? False. Is the reason not weather? False. Because the condition is logically inconsistent with the policy model, AR catches the error and returns an invalid status.
And the application then prevents the chatbot from giving the wrong answer.
It prevents the costly and incorrect refund, even though the statistical model suggested it.
That is the convergence in action. The LLM provides the friendly, conversational interface and the flexibility. The automated reasoning provides the mathematical certainty and protects the organization from policy violations or costly errors.
It's the only way to establish provable correctness across complex, interconnected policies that define compliance, financial, or security decisions.
So this combination of GenAI drafting and AR verification is rapidly accelerating security efforts across several key domains. Let's look at the top security use cases for automated reasoning.
The first major use case is incredibly impactful in a world generating more code than ever: code generation. When an AI generates source code, that code can be automatically verified for crucial security properties using AR-based program analysis tools.
And what are we proving here? Not just that the code compiles, but that it's actually safe.
Exactly. We are proving properties like memory safety, guaranteeing no access outside allocated bounds, the absence of buffer overflows, and the correctness of input validation routines. This verification is essential for highly secure systems.
And we're seeing tools for this already.
We're seeing growing frameworks in languages like Rust, with tools like Kani and Virus that use underlying AR engines to formally verify code safety. This is a game changer for supply chain security.
The second area is infrastructure configurations. These are notoriously complex and often where misconfigurations lead to major breaches.
AI-generated cloud configurations, network topologies, or deployment scripts are often complex YAML or JSON files that contain infinite possibilities for misconfiguration. AR tools can model those configurations and verify them against high-level security policies.
Like the AWS Reachability Analyzer.
I mentioned that earlier. It uses a formal reasoning engine to check complex virtual private cloud, or VPC, configurations. It doesn't test if a connection works once. It mathematically certifies that under any possible scenario, a sensitive private database is inaccessible from the public internet, thereby enforcing the policy.
So it moves beyond testing into certified compliance with the security policy. The third area, and maybe the highest priority for zero trust architecture, is authentication and authorization policies.
This is a perfect fit for AR. AI is increasingly used to generate IAM policies, role-based access control rules, or complex authentication flows. These systems are inherently about logic. If X is true, then Y is allowed. We need to verify that these AI-generated policies are consistent, complete, and adhere strictly to the principle of least privilege.
And we're seeing this in practice with tools like Cedar.
Exactly. Amazon's open source authorization policy language, Cedar, which powers Amazon Verified Permissions, uses verification-guided development based on automated reasoning to assure developers that authorization decisions will be correct under all circumstances.
And the synergy here is incredible. Amazon Q Developer can generate Cedar policies from a simple natural language prompt, and the AR system ensures the resulting policy is logically sound and compliant before you deploy it.
It creates this frictionless path from intent to certified correctness. Finally, AR is highly useful for compliance documentation and answering due diligence questions. While RG systems retrieve content, the LLM-generated summary answers often hallucinate.
I can see that being a big problem.
A huge problem. AR can build a semantic model of the compliance knowledge base and then validate the AI's answer against that model, catching inaccuracies that would lead to non-compliance.
While AR offers this certainty, we have to be realistic about the challenges in adopting it. It isn't a universal solution just yet.
Not yet. We have to be clear-eyed about the limitations.
For one thing, AR relies on assumptions.
That's a crucial point. While AR proves the correctness of the logical model, that model sits atop certain environmental assumptions, that the operating system behaves as expected, that the hardware isn't compromised, or that the compilers and processors have no bugs.
So you can't abandon traditional end-to-end testing.
You can't. You still need that testing to validate those underlying environmental assumptions, not to verify the logic itself.
The second issue is that AR needs definitive, unambiguous rules.
Formal logic is unforgiving. It can't handle specifications that are too vague, subjective, or ambiguous to be expressed in mathematical logic. However,
There's a silver lining here, isn't there?
there is. The rigor required to build a formal model often reveals and helps correct those ambiguities in the original specifications, which is a massive net positive for system quality and reliability down the line.
And finally, the expertise required to build these models is still a barrier.
It is. Applying AR to highly complex systems requires specialized expertise in mathematical logic and formal methods. That talent pool is still pretty narrow.
But generative AI is starting to help with that.
It is. As we discussed, an LLM can help a non-expert formalize their requirements into a first draft of a logic model, making this technology increasingly accessible.
So the conclusion of this section is really this strategic convergence. Generative AI provides the speed, flexibility, and the natural interface. Automated reasoning provides the mathematical certainty and security.
It's the necessary partnership for building truly secure, autonomous agentic systems at scale.
We've spent a lot of time on securing the AI itself. Now let's shift lenses to the counteroffensive, using AI to enhance our security operations and protecting against these new, sophisticated AI-powered threats.
This is how we scale our human teams.
So we have to start with the core problem, the scaling challenge. Core security tasks like application vulnerability review, manual pen testing, incident response, they're all inherently human-driven.
And the resources required just increase proportionally with business complexity. We simply cannot hire fast enough to keep up with the data volume and the alert velocity.
And meanwhile, the adversary is leveraging the exact same technology. AI-powered threats are lowering the barrier of entry for malicious actors.
It's allowing them to launch sophisticated, polymorphic, and faster attacks at a fraction of the cost, overwhelming traditional human-centric defenses.
So the solution is to invest strategically in Gen AI and specialized machine learning to enhance and accelerate our conventional automation systems.
It's about augmenting human intelligence, not replacing it.
How is this being applied in specific areas? Let's start with application security, or AppSec, which is typically a major bottleneck in development.
In AppSec, AI is fundamentally changing the speed of development and review. AI-powered security agents can automate routine tasks like searching for common code patterns, providing real-time security feedback to developers right inside their IDE.
And facilitating automated penetration testing sweeps.
Exactly. This speeds up the feedback loop dramatically.
And they can communicate with existing tools, right? We have the Model Context Protocol, or MCP, mentioned in our sources. What is that, and why is it important for AppSec?
The Model Context Protocol is an open-source standard designed specifically to allow generative AI applications to communicate securely and contextually with external systems and tools. And it's vital because the LLM agents aren't useful in a vacuum.
They need to talk to our other tools.
They need to invoke your static analysis tools, your dependency scanners, your vulnerability databases.
Right.
MCP standardizes the communication format, ensuring the AI agent can receive the necessary context from, say, a SAST tool, and then pass that information, along with its own reasoning, securely to a developer's environment or a ticketing system.
So it allows the agent to orchestrate the entire AppSec workflow without losing security context.
That's the key, that integration.
We're also seeing generative AI assistants like Amazon Q Developer accelerating custom security tooling, right?
Yes. Security engineers who need to write custom testing scripts, build new API security gates, or develop new threat models can leverage GenAI assistants to convert complex natural language requirements into functional code snippets or system designs almost instantly.
Which reduces the time spent on low-value coding tasks.
And allows security experts to focus on complex logic and architecture.
Okay, moving to threat detection and analysis. The sheer volume of data makes manual detection rules almost obsolete. AI has to match the velocity of the threat.
Manual research, correlation, and creation of detection rules are just unsustainable. GenAI can automate the research, draft initial detection rules, and streamline the validation steps. This allows security teams to respond faster to zero-day threats with fewer specialized resources.
Our sources emphasize that this isn't about one large AI tool, but a multi-layered approach. What does that combination look like in practice?
A multi-layered approach combines specialized AI models, each excelling in a specific domain. You might have one ML system dedicated to network traffic analysis, another focused on domain reputation scoring to identify malicious IPs, and a third using behavioral analytics to flag anomalous user behavior.
And the value comes from connecting the dots.
The value comes when GenAI correlates the outputs of all three systems. For example, if network analysis shows a large data transfer, but the domain reputation is fine, a human might ignore it. But if the behavioral analytics simultaneously flags that the user identity initiating the transfer logged in from an unusual geography...
Now you have a story.
Now, GenAI correlates these separate insights to identify a sophisticated internal threat that no single system could have flagged alone.
This complexity underscores why data standardization is absolutely vital. You can't correlate data if it's all formatted differently. And that brings us to the Open Cybersecurity Schema Framework, or OCSF.
OCSF is a critical industry-wide effort. It provides a vendor-agnostic, standardized schema to normalize security logs and alerts from every single tool, whether it's a firewall, an endpoint detection system, or a cloud access security broker.
And this unified foundation is what lets the AI work its magic.
It's essential because it allows advanced AI analytics to ingest, understand, and correlate data seamlessly across the entire ecosystem. With OCSF formatted data, GenAI can automatically map suspicious activities directly to MITRE ATT&CK tactics, techniques, and procedures. The TTPs instantly providing contextualized insights that save analysts hours of manual cross-referencing.
And in the realm of security operations, or ACAPS, where alert fatigue is a constant battle, GenAI promises some immediate efficiency improvements.
CCOPS benefits immensely. GenAI can take isolated alerts from multiple sources, a cloud log, a network sensor, an identity system, and automatically create comprehensive, context-rich narratives of an incident. This overview drastically improves investigation efficiency and response times.
So an analyst doesn't have to piece together fragmented clues.
Exactly. The AI presents the story, allowing the analyst to focus on judgment and remediation.
What are the specific measurable functions we're seeing automated in the SOC?
Well, AI is rapidly augmenting teams by automating alert triage in SIEM and source systems, ranking alerts by urgency and potential impact. It's providing real-time, context-aware guidance during active SOC investigations, suggesting next steps or necessary forensic commands, and critically, it supports analyst training by simulating complex scenarios and providing immediate, personalized feedback.
It frees up your seasoned experts for the high-value strategic tasks.
That's the goal.
Finally, let's look at vulnerability management, which can be an enormous time sink, particularly with CVE analysis.
Oh, CVE analysis is paralyzing due to the sheer volume and complexity. To properly analyze a single common vulnerability and exposures entry, and that includes assigning an accurate CVSS score and determining the vector string, a trained engineer needs to spend over an hour meticulously reviewing complexity factors, attack vectors, and potential impact.
And this process requires weeks of specialized training.
It does, and it's just not scalable when thousands of new vulnerabilities are disclosed annually.
So how does AI transform that?
The efficiency gain is transformative. A contextually grounded Gen AI-based CVE analyzer trained on reliable security data and formal standards can reduce that comprehensive analysis time from hours to seconds. It provides consistent scoring and detailed impact narratives, allowing security teams to patch and prioritize vulnerabilities at the speed required by modern business. It's a massive help in addressing the scaling challenge.
We've covered the security of the AI and the utility of the AI. Now, we have to pull back and look at the strategic organizational framework needed to govern all these practices.
And this starts with the architectural strategy. We established that no single control is sufficient. Therefore, we have to adhere strictly to defense in depth.
Did.
It demands multiple, layered defenses policy, data protection, application protection, network, infrastructure, identity, and access, all built upon a solid baseline.
The interconnectedness is key here. The layers have to reinforce each other.
Precisely. If one control fails, the next layer has to catch it. For agentic AI systems, this means that the identity and access management controls must integrate seamlessly with infrastructure protection. For example, if an agent uses a specific tool, the network layer has to simultaneously verify that the agent's identity and its current behavioral context align with the allowed usage policy for that tool.
So they aren't independent barriers.
No, they're a mutually reinforcing security framework designed to limit the blast radius.
And complementing defense in depth is the zero trust architecture.
Zero Trust strengthens DD by shifting the focus away from trusting traditional network perimeters. Instead, it assumes no implicit trust and requires continuous adaptive verification. For AI, this means applying granular policy-based access decisions based on continuous context, the agent's identity, the data it's accessing, the system state, and its real-time behavior.
That level of continuous adaptive policy enforcement seems crucial when an autonomous agent is making thousands of sequential decisions.
It is absolutely crucial.
Even with the best technology and architecture, though, the defense is only as strong as the people running it. AI upskilling is non-negotiable.
Security teams risk falling dangerously behind the curve if they don't continuously adapt.
This requires a cultural shift, doesn't it? Fostering a learning environment that encourages hands-on experimentation and transparency. People need to feel safe to test new AI tools and share both their successes and their inevitable failures.
To build an effective upskilling strategy, organizations have to take several strategic steps. First, collecting granular feedback from employees about the specific AI skills they are missing or need the most. Second, aligning learning efforts directly with both security and core business objectives.
And setting realistic, measurable goals.
Yes. For example, by Q4, 75% of SOC analysts must be proficient in using GenAI to draft MITRE AT and CK narratives. You also need to tailor learning approaches.
To cater to different learning styles.
Exactly. This means mixing formal training with hands-on, on-the-job mentorship, self-paced courses, and high-impact technical workshops. And finally, organizations must regularly conduct skills audits and gap analyses to measure the effectiveness of the training and ensure their human capital is evolving alongside the technology.
The final crucial organizational layer is governance and compliance. The global AI regulatory landscape, from the EU AI Act to various state-level U.S. laws, is evolving so quickly that compliance teams feel like they're trying to hit a moving target.
They are navigating a complex, multi-jurisdictional maze. AI governance refers to the comprehensive set of frameworks, policies, and processes designed to align AI development and deployment with business objectives, regulatory requirements, and ethical standards.
And the most robust strategy isn't chasing every new regulation, but focusing on the core principles of responsible AI.
That is the anchor. If you focus on verifiable, repeatable, responsible AI principles, you build a resilient program that can map onto new regulations as they emerge, rather than building bespoke programs for every jurisdiction.
Like the 8 core dimensions AWS uses.
For example, yes, they serve as an excellent operational checklist for what comprehensive AI governance looks like.
Let's detail those 8 dimensions.
They include controllability, mechanisms to monitor and steer system behavior, privacy and security, which is protecting the underlying data and models, safety, preventing unintentional harm, fairness, mitigating bias,
Okay.
then veracity and robustness, which is achieving consistent, correct output even against adversarial inputs, and that requires AR explainability, understanding why an AI made a certain decision, transparency, enabling users to make informed choices. And finally, governance itself, ensuring these best practices are incorporated across the entire AI supply chain.
Implementing globally recognized voluntary standards like the NIST AI Risk Management Framework or ISO 42001 helps organizations adopt these principles effectively.
And it provides a map for their existing compliance controls.
To make this governance framework actionable, organizations have to implement several key best practices. The first is maybe the most fundamental: AI discovery and inventory.
This is about knowing what you have. You have to build a comprehensive inventory that goes far beyond obvious applications like customer chatbots. You need to identify AI components embedded within traditional applications, third-party AI services, and, most critically, AI systems that may be in your supply chain.
And you have to address shadow generative AI.
You do. Many organizations discover vast areas of unauthorized usage by employees using public tools for proprietary tasks. You need monitoring dashboards and endpoint solutions deployed specifically to detect and track this unauthorized shadow usage.
The next crucial practice is conducting thorough risk assessments, which have to expand beyond traditional cyber factors.
Traditional risk assessments focusing on data protection and confidentiality just aren't sufficient anymore. AI systems introduce entirely new risk categories that have to be explicitly evaluated. Societal impact, bias, and fairness implications, risks related to model drift where accuracy degrades over time, and the potential for excessive autonomous behavior if controls fail.
Third, organizations have to establish clear, unified policies and procedures.
These policies need to provide organization-wide requirements for building and using generative AI services, aligned with existing data classification, security, and legal policies. The policies have to clarify permitted versus forbidden uses and communicate the acceptable risk level for different scopes of deployment buyer versus builder.
Number 4, documentation. You can't stress this enough for compliance.
Thorough documentation is essential for demonstrating compliance and ensuring operational consistency. You have to maintain clear records of every AI system, the result of risk assessments, detailed development procedures, the training data used, and ongoing monitoring protocols. The security controls, especially the specific guardrails and verification steps like automated reasoning outputs, must be documented.
Fifth, defining roles and responsibilities. Who owns the risk when the agent acts autonomously?
You have to define clear oversight roles from the executive level down to the technical leadership. And critically, you need to clarify the shared responsibility model in AI compliance with your vendors. You have to have a clear contractual understanding of your obligations versus those of your service providers.
Including specific requirements for incident response and vulnerability management.
Yes. And finally, continuous monitoring. Since the landscape is moving so quickly, static point-in-time assessments are insufficient.
So you have to stay informed.
You have to stay informed about global regulatory changes and continuously assess your AI systems for compliance against evolving standards. Implement robust feedback loops. The goal is to promote governance not as bureaucratic overhead, but as an enabler of safe innovation.
As we wrap up this deep dive, the central strategic question remains: how do we effectively enforce security principles at scale while preserving human judgment when it matters most?
It's about defining the balance between AI automation and human oversight.
The key is establishing clear, defensible boundaries.
Exactly. For routine, well-defined tasks with limited potential for harm like classifying threats based on known signatures, providing initial context, or blocking malicious activity that follows established patterns, A high degree of AI autonomy is acceptable and necessary for scaling.
But when the potential impact is high, human judgment must be required, even if the AI has provided a statistically sound recommendation.
Absolutely. The source material provided a strong principle here. The higher the potential impact of a decision, the more human oversight should be required. For instance, at Amazon, AI is not allowed to autonomously shut down critical production services, execute major configuration changes, or take actions that substantially impact customers without human verification and sign-off.
So the AI can detect, recommend, and draft the response.
But the human expert retains the final veto and responsibility for the action that's taken.
This is the optimal partnership. AI excels at analyzing patterns, processing data volume, and generating context. Humans provide the necessary contextual understanding, ethical judgment, and creative problem-solving required in ambiguous or high-stakes situations. This has been an incredibly detailed look at the dual challenge of securing AI systems and leveraging them for our defense. To leave you with actionable direction, we've distilled all of this into 3 key action items for you to take back to your organization.
Action item 1, securing generative AI. Immediately determine the scope of your implementation. Are you primarily a buyer consuming services, or are you a builder creating custom models? This scoping decision dictates the shared responsibility model you have to implement, and it drives your security control implementation. It ensures you focus resources where your risk is highest.
Action item 2, using generative AI for security. Identify 1 or 2 existing security bottlenecks where AI augmentation can provide immediate, measurable scaling benefits. Things like automating CVE analysis or triaging SOM alerts, and focus on standardized integration using frameworks like OCSF to ensure your data foundation is ready for advanced correlation.
And action item 3, protecting against generative AI-powered threats. You have to stay ahead of the adversarial curve. Continuously monitor emerging AI-generated attack vectors and TTPs, and update your threat models accordingly. Invest in AI-based detection and response capabilities that can match adversarial speed and scale, but always integrate those capabilities with appropriate human oversight for critical decisions.
We've covered the entire journey. Securing the core application, leveraging the technology for defense, and managing the risk through strong governance, defense in depth, and responsible AI principles, all anchored by the certainty of automated reasoning.
Success in this new landscape requires a dynamic, iterative approach. You have to view AI not as a static tool, but as a living system requiring continuous governance and maintenance. Forging that human-AI partnership is the key to creating robust, adaptable security programs that manage risk while truly enabling innovation.
And that leads us to our final thought for you. We just discussed how automated reasoning can mathematically prove the correctness of complex systems, from authorization policies to cloud configurations, providing absolute certainty.
So consider this. What is the highest impact operational decision your team currently makes manually, a decision requiring hours of cross-referencing and human sign-off that, if formally verified by automated reasoning, could be safely entrusted to an autonomous, provably correct agent tomorrow?
That challenge forces you to bridge the gap between AI flexibility and mathematical certainty in your own operations. Something to think about until our next deep dive. Thanks for joining us.